Hello, my name is Daniel Stolfi from the University of Luxembourg. I am presenting our research work, Optimizing Autonomous Robot Swarm Parameters for Stable Formation Design. First, I will introduce our research topic. Then we present the robot formation approaches, followed by experimental results, and finally conclusions and future work. Robot formation is all about coordinating swarm of robots to achieve a common goal. They could be self-organized or follow predefined shapes to perform collective tasks. These tasks can be surveillance, salvage missions, mapping an uncharted area, or displays as shown in the figure, etc. The research work presented here concerns the basis of swarm formations for two main applications: asteroid observations, in which collisions with the object of interest have to be avoided while observing the maximum surface, and escorting a rogue drone out of a restricted area, such as an airport, using a swarm of drones which surrounds the intruder and force it to move out of the area. We want to achieve this formation using autonomous robots in a decentralized approach, using only their relative positions once the central object of interest has been identified. Different approaches can be used for robot formation. The geometric approach is a naive strategy in which the distance between robots and between each robot and the center are calculated. After that, each controller will try to achieve a successful formation using these parameters. Our approach consists of using the formation algorithm, which pseudocode is shown in this slide. Each robot will transmit a beacon signal and receive the beacons from the other members of the swarm. Using these signals, they will know the relative angle of the other robots and their distance, what is usually called range appearing. For the model, there is a ghost robot in the center of the formation, which is to be used as a reference, matching the position of the object of interest. Finally, there are two sets of attracting or repelling forces per robot, one concerning the rest of the swarm and the other from to the ghost. As it can be seen in the algorithm, this center is a predefined parameter which indicates the desired distance to the center of the formation to be achieved by the robots. And the robot, which is used as a threshold to apply an attracting or repelling force between robots. As a result, the next moving direction is calculated and used by each robot controller. We propose a genetic algorithm to optimize the swarm parameters, the distance between robots and the number of ghosts at the center. We have experimentally set up the algorithm parameters as well as the problem constraints. We have evaluated each swarm configuration using these functions. The function p calculates the accuracy of the polygonal shape, while epsilon minimum and maximum are the relative errors with respect to the desired distance to the center. These terms are averaged by evaluating 28 different scenarios to achieve a more general solution. Additionally, there is a penalization term which tries to keep the number of ghosts as low as possible. The objective of the genetic algorithm is minimizing f, so the lower the better. In order to evaluate each configuration, we will use the ARGOS simulator. We propose 4 case studies featuring 3, 5, 10, and 15 robots. 28 scenarios per case study will be used in the optimization process, and the best solution will be tested on another 72 unseen scenarios to check its robustness. We have obtained our results using this procedure. We have optimized 4 case studies by doing 13 independent runs of the genetic algorithm per case study. The best configurations were tested on 72 unseen scenarios, and the achieved results are compared with 2 other approaches: the aforementioned geometric approach and another approach in which no ghosts were used to address the need of having at least one ghost to position in the swarm. After the optimization process, we have achieved the results shown in this table. We can see that the perfect formation was achieved for 3 robots, and that for 10 and 15 robots, more than one ghost was needed to achieve a stable formation. Then we have tested the best configuration on 72 unseen scenarios per case study and compare our results with the other 2 approaches. We can see that our formation algorithm has worked properly in all the scenarios and case studies, achieving distances to the center very close to the desired 1.0. These results can be easily seen in this graph for 3 robots and 72 scenarios. In this case, the geometric approach and our optimized approach achieve the same successful formations. It can be seen that for 5 robots, the geometric approach is not keeping the desired distance to the center. For 10 robots, only our approach is working properly. And the same can be observed for 15 robots. These are snapshots taken from ARGOS showing the formations achieved for one scenario. Now we wanted to go a step further and test our proposal using real robots. We have used the Epoch-2 robots equipped with proximity sensors and 2 motors as members of the swarms. We have set up this experiment using a board for the robots and a video camera. Using ARGOS markers on each robot and OpenZV, we will simulate the range appearance sensor of the Epoch robots to be used with our formation algorithm. Even though the environment provides the absolute position of each robot, we have not used it, as our system is supposed to achieve stable formation without knowing the absolute position of each swarm member. We can see a short video of the robots building the formation using our algorithm. We have only scaled the values obtained by the genetic algorithm to the new distance to the center. A full video showing more scenarios is available at adars.uni.lu. As conclusions of future work, we have proposed a new formation algorithm. We have optimized its parameters using a GA. Several ghosts were needed in the more complex scenarios. Our approach has achieved stable formation in the 288 unseen scenarios. And we have also validated our proposal using real robots. Our next steps consist in adding more robots and replacing the central ghost by the new force, and also continue moving towards our final objective, which is adapting our algorithm to a 3D model. As you can see, we have already taken some steps and we have some working prototypes. Thank you for your attention. Please contact me if you have any further questions.